Good afternoon, class. Today we'll be looking at Chapter 8. In Chapter 8, we finally move away from triangles. We're going to look at just general shapes, in particular polygons. But we're going to take a focus on quadrilaterals for this chapter. The first thing we're going to look at is actually going to be very generic. It's going to be about diagonals. A diagonal is a segment that connects any two non-consecutive vertices in a polygon. What that means is if I would take one vertex to another, as long as they're not consecutive, right next to each other, right in a row, it'll be a diagonal. In the picture on the PowerPoint, you see this shape. Now, this point here are consecutive vertices. If I drew a segment connecting those consecutive vertices, I'd get a side. This is a side. But if I would connect two other vertices, let's just say this one here and this one here, they're not consecutive. They're not the next two in order. So for instance, they're not in order as I count around. 1 and 4 are not numbers right next to each other, so it's non-consecutive. If I would connect a line connecting those two vertices, that would be a diagonal. Now, in a in a shape like this, there's multiple vertices. In fact, I could draw 3 diagonals from one vertex up here. This and this point would be a side, and this point would be a side. So those are all the vertices I could draw from that one. Sorry, not all vertices. All the diagonals I could draw from that vertex. If I did the same thing here, 1, 2, 3. If I did the same thing over here, I already have one drawn. I could draw another one here, another one here. Here I already have 2 drawn, so I can draw one more. I look at this one, all 3 are drawn, all 3 are drawn. This is how many diagonals are in this one picture. Now, when we look at diagonals for our case, unless we're talking about quadrilaterals, we're generally only going to look from diagonals from one vertex. So even though I drew a whole bunch here, when I look at a different polygon, let's just say this one over here, if I was going to look at diagonals, I'm generally only going to look from one vertex. So this would be a diagonal, this would be a diagonal. Now yeah, there ends up being somewhere around 6, I believe. 2, 4, 5, my bad. But I'd only draw those 2 because of the next theorem, and that's why we introduced diagonals now. But the difference between a diagonal and a side is a side connects 2 adjacent or 2 consecutive vertices. They're right next to each other. A diagonal connects 2 non-adjacent or 2 non-consecutive vertices. The first concept is the polygon interior angles theorem. What it says is the sum of the measures of the interior angles of a convex n-gon is 180 degrees times n minus 2. I look at this. The 3 shapes I have, n equals 3. So if I would plug 3 into that formula up there, 3 minus 2 is 1. 1 times 180 is 180. Yeah, a triangle has a measure of 180 for all the interior angles added together. N equals 5, the pentagon. Well, 5 minus 2 is 3. 3 times 180 is 540. Yeah, so all the measures of the interior angles of a pentagon have to add up to be 540. And last but not least, the hexagon over there, n equals 6. 6 minus 2 is 4. 4 times 180 is 720. That's how I know the measures of the interior angles of each of those polygons. Now, the way to justify it or show it to you is by using diagonals. And it's also the way I can show you how we came up with this formula. If I would look at, for instance, a pentagon here, I already know that all of the angles, or the interior angles of a triangle, add up to be 180. So what if I divided this shape here into triangles? So I choose a vertex. Let's choose this one here. I'm going to draw it here. Triangle 1. I'm going to draw it here. Triangle 2. And this ends up being my third triangle. Now, if each triangle, all the interior angles add up to 180, and there's 3 triangles inside of this shape, Well, then 3 triangles times 180 is 540. Or in other words, I take the degree measure of a triangle and I multiply it by the number of sides minus 2. Because that's how many triangles I'm going to make. Let's just check real quick if this formula works, or this idea works. Let's draw a hexagon. There's 6 sides, right? But let's see how many triangles this can break up into. So I choose a vertex, 1 triangle, 2 triangle, 3 triangle, and 4 triangles. So there's 4 triangles. So I'm going to take 4 triangles times 180. I get 720. The formula 180 n minus 2 works yet again. All you take is the number of sides minus 2, and that tells you exactly how many triangles you can draw on the inside right there, and then you just multiply by 180. If you ever forget the formula, you know all the interior angles of a triangle add up to 180. So divide your shape into triangles, multiply 180 times the number of triangles you have. Done. Alright? But let's look at a few examples here. The first example says the sum of the measures of the interior angles of we'll hold off looking at examples for now until after we get this theorem down. And the last thing on here, I said the formula to find the measures of the interior angles of a polygon is this formula. That's true. But because this chapter is all about quadrilaterals, there's a corollary to this which quickly says the sum of the measures of the interior angles of a quadrilateral is 360. Honestly, this theorem here is the overriding one. It's the big one that tells you for every single polygon. But we're going to be specific right now because we're looking at quadrilaterals in this chapter, so this is the one that's important to us. So if I see a quadrilateral, anything with 4 sides, I know that all the interior angles add up to 360. Now let's look at a few examples. The first example says, find the sum of the measures of the interior angles of a convex octagon. Alright, in example 1, I'm trying to find the interior angles here. I gave you 2 options up here. The first one, we're just going to use the formula. The second one, we're going to use the ideal behind the formula. We're going to see that we get the same answer here, but I'm going to give you 2 options. Now the nice thing about the formula is when the number of sides gets huge, you won't have to rely on the visual side. The nice thing about the visual side is it's a picture. You can actually see what's going on. So this one, the formula is the sum of the interior angles is 180 degrees times n minus 2. So 180 degrees times 8 minus 2. 8 minus 2 is 6. 180 degrees times 6. 1040. Those of you that snowboard, it'll be a little bit easier for you to do this because you're more used to saying, all right, 6 half turns is 3 full turns, 3 full turns is 1040. Actually, hold up. What am I thinking? It's not 1040, it's 1080. All right, this one over here. Because I've already drawn the diagonals, it's going to be a little bit quicker. But there are 6 triangles. Each triangle has 180 degrees. 6 times 180, 1080. Now, this one would normally be a little bit longer just because you actually have to draw the diagonals, and you have to count the triangles. But I had already done that for you, so it looks like it might be quicker, but it actually isn't. Using the formula over there, it's a lot quicker. But that formula is using this idea, and that's how we get it. Example 2. The sum of the measures of the interior angles of a convex polygon is 2,160. Classify the polygon by the number of sides. So the last question I had asked, alright, I give you a certain number of sides, what's the measure of the angles? But in this case, I'm actually saying, hey, I know the sum is 2,160. What polygon is this? Alright, at this point, I don't know what shape it is. But I know that 160 has to be a multiple of 180. Now, I could try doing this in some other way than using the formula, but let's use the formula. I know 180 times n minus 2, well, that's the sum of the interior angles. But I already know the sum is 2,160. So at this point, now look, why don't I just solve for n? The furthest thing out on this side from n is 180, so let's divide both sides by 180. And I end up getting that this over here ends up being 12. And then add 2 to both sides, I get n to be 14. So if I had to classify this by the number of sides, I'd call it a 14 gon. That's all there is to this one. Classify by the number of sides. They're asking you to just plug it into the formula, but go the opposite way. Instead of plugging n in, you're solving for n. And once you get n, you classify it that way. Example 3. Find the value of x in the diagram. If I look at this diagram, I've got a 5-sided polygon. I'm given 4 of the 5 angles, and I'm asked to find the last angle. So, let's redraw this picture first of all real quick. Now, I wish I knew what all of the angles of a pentagon added up to be. But I know that if I would add them all together, I should get a set number every single time. Unfortunately, I don't know what that number is right now. If I knew that number, I could just solve for x by adding all those together and subtracting the number from the total. Which, real quickly, let's do this. That would be x plus, well, let's see, that's going to be 130 in the middle there. This will be 296, 396, x plus 396. But I don't know what that equals yet. So if I knew the total sum of all the angles added together, all I'd have to do is set that equal to it and solve for x. So what does the sum of the angles of a pentagon add up to be? Well, for a pentagon, n is 5. Well, if I did 180 times n minus 2, well, that's saying 180 times 5 minus 2, which is 180 times 3, which is 540. That's what all the angles of the triangle add up to be. Not the triangle, my bad. All the angles of the pentagon add up to be. So when I add them all together, I should get 540. I should get 540. I should get 540. Now look, at this point, if I know that they all add up to be 540, and I know that this is also the sum from this part over here, to find x, all I have to do is subtract 396 from it. So x equals 144 degrees. That's it. If I give you a problem and I say find the value of x, now it doesn't matter if it's a triangle, a quadrilateral, pentagon, octagon, 1,000 gon. If they gave you enough angles, every one but one of them, you should be able to tell me what that measure is simply by, first of all, finding what all of the angles should add up to be, and then adding all the angles together and solve for x. Alright, the last idea or theorem from this section now steps away from the interior angles, and we're going to look at the exterior angles. If you remember back to triangles, the exterior angle is the angle formed by extending one of the sides of a polygon. So if we look at this picture here, all those angles there, 1, 2, 3, 4, and 5, those are all exterior angles because the ray extending from the side, this one right here, and the side form this angle, which is what we call the exterior angle. Now, there is actually 2 over here, but I didn't extend this side, but this angle here and this angle here would have been the same angle. I only drew one of them. But this says the sum of the measures of the exterior angles of a convex polygon, one at each vertex, is 360 degrees. So if I would add 1, 2, 3, 4, and 5, all those angles together, I would get 360. In fact, it doesn't matter what polygon. It could be a hexagon, it could be heptagon, octagon, nonagon, a bajillion gon, although I'm pretty sure bajillion isn't a number. But you get the idea. Now, if we just took a real quick approach at this, if I would have something like a triangle here, if I would extend each of these angles here, sorry, each of these sides, 1, 2, and 3. Now let's pretend I zoomed out a little bit. I walked further away from this polygon. So it's going to look a little bit smaller. But angle 1 would still be here, angle 2 would still be here, and angle 3 would still be here. Now let's pretend I just walked away a little bit further. And I walked just a little bit further. And I walked even just a little bit further away. Eventually, it would look like this, with angle 1 being here, 2, and 3. And look, all those angles essentially would go all the way around. And that there would mean it's 360. In fact, if I moved away from any shape, eventually the shape itself would form a point in my vision. And if I kept extending these lines, what I'd eventually see is this here, where it looks like it's just 3 lines going forever. Because the exterior angles will form this sort of shape. If I add more sides, it's just going to make it look a little bit different. But all those angles that I add together will still be 360, because when I get far enough away, it's going to look as if the shape is just a point, and all those angles extend. So that's why my argument is it would be 360. It doesn't matter if it's a triangle, a quadrilateral, pentagon, it's 360. And this is my reasoning why. There's a more formal proof. I'm not going into it. But there you go. So let's look at this. We have a pentagon again. Oof. Does that mean I have to find the value of the sum of the interior angles? Well, first let's read the problem. It says find the value of x. Alright, so pretty simple problem. At least in phrasing of question. Now, I look at here. What am I all given? Well, this angle, this angle, this angle, this angle, and all 5 of those angles are exterior angles. Whoa. All 5 of those are exterior angles. And it's a pentagon, so it has 5 exterior angles. Wait, so I have all the exterior angles of this polygon? In fact, what I'm looking for is the exterior angle. Why don't I just add up all these exterior angles and set it equal to 360? It doesn't matter what the shape is. The sum of all of them will equal 360 every time. So let's just start with x and go counterclockwise. X plus 100 plus 35 plus 60 plus 75 equals 360. I'm trying to solve for x, so let's simplify this a little bit further. X plus 270, I believe, if done correctly, equals 360. Subtract 270 from both sides. X is actually a right angle here. That's it. So all the exterior angles will always add up to be 360. To find out what the sum of the exterior angles is, interior angles, I have to use this formula. So this is interior angles, and this is exterior angles. Alright? Those are the 2 basic ideas you need to know. And in fact, I've covered almost everything I need to for this section. But there's one last type of question I'm going to throw at you, so let's go over an example of it. We're going to deal with a pentagon again. I know we've dealt with it a few times here, so you're probably almost going to get sick and tired of hearing about it. But find the measure of each interior angle of a pentagon and the measure of each exterior angle of a pentagon. Oh, wait. Didn't I do this before? The sum of the interior angles of a pentagon is 540, and the sum of the exterior angles is 360. Am I done? Well, unfortunately, no. If I look at the question, there's a key word that says each, and that means I have to find it for each individual angle. It's a regular pentagon, which means all the angles are the same. It also ends up meaning that all the exterior angles will be the same. Now, there are 2 ways to do this, and I'm going to do both ways, just to give you an idea of what you could do to approach this problem. I honestly think option 1 will be easier. If I ever ask you to find the measure of each interior angle of a pentagon, this is how I'd go about it. I'd first find the measure of each exterior angle. Well, why would you say that? Well, if I add up all of the exterior angles, y plus y plus y plus y plus y, I already know what that equals. I don't have to do any calculation. I just have to remember that all of the exterior angles added together is 540. Add all the y's together, I get 5y equals 540. I'm going to pause right here for a little bit. 5. Number of sides or number of angles in that polygon. Whoa. What am I doing here? 360. Because all the exterior angles always add up to 360. This adds up to 360. So I'm doing the exterior first. 5 is the number of sides or the number of angles. 360 is what the exterior angles always add up to be, no matter what the shape. So if I want to find each of them, all I have to do is take 360 divided by the number of sides. Y equals 72. Each exterior angle is 72. Now let's do interior. Hold up. Let's look at x and y here. This right here is a straight line. If that's a straight line, that means x plus y is 180 degrees. X plus y equals 180. Because it's a linear pair, they both add up to be 180. X plus 72 equals 180. X is 108. I found the exterior angles and interior angles. That's the first option. I think this one ends up being a little bit easier. This is the option I would approach it this way. Option 2, instead of finding the exterior angles first, you could find the interior angles first. Alright? Now the addition of all of the interior angles will be x plus x plus x plus x plus x. And that's going to equal some number over here. Well, it's going to be 180 times n minus 2. Well, n is the number of sides, 5 minus 2. So I look, this is 180 times 3. And this is going to be 5x. 5x equals 540. And now I look. Number of angles, or number of sides, the sum of the interior angles. Take the sum of the interior angles, divide by the number of sides, and that's what I will get for each angle, 108. So I just found the measure of each interior angle. Now, we're going to use the same reasoning. X and y is a linear pair. So in this case, why don't I do x plus y equals 180. 108 plus y equals 180. Subtract 108 from both sides, I get 72 to be y, and I just found the exterior angles. Now, this one there is a few more lines of work. I also think this one's a little bit tougher conceptually. Take the measure of each exterior angle here, or sorry, the sum of the exterior angles, divide by the number of sides, you get the measure of each exterior angle. Take this, subtract it from 180, you get the measure of each interior angle. This is a lot easier, I think, to do than finding the measure of each interior angle and then finding the measure of each exterior angle. I have seen some people do it this way and this way each time. That's fine with me. You will get it right. But you're going to have to do either option 1 or option 2 or the first part of both options. It's your choice, but I think option 1 is the best. And I think that's all I have for today. So, till next time.